Hello everyone, my name is Vishal. I'm a data analyst transitioning into machine learning research, and this is my channel where I'm documenting my entire journey. I'm passionate about tiny models, resource-constrained research, and understanding deeply how things work. In this video, I'm going to walk through my second round of Imagenette results. Imagenette is a fast AI dataset, which is a 10-class subset of the Imagenette dataset. It's about 10,000 images. And then I'm also going to share my takeaways from Gemini's deep research report on the challenges and solutions to small batch size training. So that's a quick background. I did some initial experiments, and I have a previous video on that where I was just trying out for a fixed batch size of 64. I was trying out a few different learning rates, 1ENEG4, 1ENEG3, and 1ENEG2 for 3 different models, xresnet 34, xresnet 18, and xresnet 50, and just trying to get some initial sense of what the training looks like and what the results are. And these were the accuracies that I got. 0.7929 was the highest. And there was this kind of hierarchy where 1ENEG2 had the best performance, followed by 1ENEG3, followed by 1ENEG4. But these were kind of quick and dirty experiments. I just wanted to get things running and get a sense of how things work. So in this notebook, I'm expanding that, and I'm showing my results for batch sizes from 1 to 2048. And then for each model and each batch size, I used FastAI's LR-Find to find 3 stable learning rates. So if we look at the raw data, this is from weights and biases, I have my run name, and I made the run name so that I could extract the model, batch size, and learning rate. And then here's the maximum accuracy that was obtained during that run. So in total, there's 123 runs. And if we look at the best run overall in terms of maximum accuracy overall, the xresnet 34 was the best model, batch size of 16, and a learning rate of 1ENEG3. And then if we look at the top 10 learning rates, the top 10 runs based on accuracy, then we see a couple of patterns. Number one, all of the learning rates are either 1ENEG3 or 1ENEG2. So those were the 2 best performing learning rates. Second thing we see is that most batch sizes are 8, 16, or 32, although we do have a 64, a couple 64s, and a 128. But largely, small batch sizes were higher performing. And this was something that I was interested in seeing, and I posted a question on Twitter, and let me see if I have it here. No, I don't. But basically, I posted a question on Twitter that, how low can you go when it comes to batch size? And that's something that I'll talk a little bit more about when we talk about the Gemini Deep Research Report. I think that's everything I want to show for the top 10. Yeah. So when we look by model, they all kind of get the same maximum accuracy or similar. They're within 1.2% of each other. However, xresnet 50 did not fall in the top 10 configurations. So that's something I think that's a little noteworthy. If we look at batch sizes, 16, 32, 64, 8, and 128, all are within 1% accuracy. So I consider that, a pretty tight grouping. And then you fall off a little bit as you go down, but you really fall off at 1024, 2048, and 1. So my takeaway from this is that very small batch sizes and very large batch sizes lead to worse performance. And we'll see that trend more concretely and more visually in a second. If we look at learning rates, there was 6 learning rates that I tried based on how stable they were for different batch sizes. And 1ENEG3 is the almost clear winner, although 1ENEG2 is right behind it. 1ENEG4, there's an 8% drop, and then there's a significant drop. So 1ENEG3 and 1ENEG2 are kind of the 2 clear winners when it comes to learning rates across batch sizes. So this is when it starts getting interesting. So I'm going to look at the comparison between learning rates, which are the 3 curves, blue, orange, and green. Batch size is on the x-axis in log scale, and then the y-axis is the final accuracy that was obtained, which is the maximum accuracy in this case for all of my training runs. So we see this clear pattern for each learning rate where you start out low at 10 to the 0, so batch size of 1 or 2, depending on the model. In this case, this is the xresnet 18, so we start at 1, which is here. And then as the batch size increases, the accuracy increases. And then it kind of plateaus. And then once the batch size goes past about 64 or 128, depending on the learning rate, the accuracy significantly drops. And we'll look at a couple other patterns, but for now I just want to make note of this general pattern that we see. And we see it in all three models. Here's xresnet 34. The smaller learning rates were stable based on LR find, but looking at this plot, really poor performance by these small learning rates. But still, we kind of see this kind of U-shaped curve where we have a increase followed by a plateau followed by a decrease. This is xresnet 50, which is a little different, right? You still get that initial increase as batch size increases. You get that initial increase of accuracy, but then it kind of plateaus and it never really comes down. So this could be for a number of reasons, but maybe the batch size wasn't large enough, and maybe if we did a large enough batch size, it would come down. But I think it's very noteworthy that xresnet 50 was more robust to batch sizes after a point, right? After you go past like 16, the accuracy is relatively stable, compared to what we see as a large cliff for some of these here for xresnet 18, 34, and then 18 here. But overall trends, too low a batch size and too large a batch size, performance accuracy worsens. And there's this kind of sweet spot depending on the model, but somewhere between 8 and 64. Okay. So I'm going to talk about next steps real quick, but I was kind of musing on Twitter that how low can you go? And Jeremy replied and said, that's a great question. Stable, low batch size training isn't easy, but it's a good plan. And so that made me think okay, this is worth pursuing. I got to take that signal and I got to act on it. And I hadn't used Gemini Deep Research up until that point. And so I thought this would be a really good opportunity to do so. At the same time, I also prompted Allen AI's Paper Finder. And I said, I'm looking for strategies to make low batch size training more stable and improve accuracy for image recognition. And the papers that it referenced in Paper Finder were included in the papers that Deep Research referenced as well. So I just kind of did that as a quick kind of sanity check on what Deep Research was finding. And looking through Deep Research's report references, there was a lot of good material in that. So I'm going to walk through this Deep Research report at a high level in some cases, and then in some cases go into some more detail. But here was my initial prompt. I recently have been training xresnet 18, xresnet 34, and xresnet 50 on the Imagenette dataset by FastAI. I've trained on batch sizes from 1 to 2048. Generally speaking, the highest accuracy achieved increases from a batch size of 1 to 8, 16, or 32, and then decreases as batch size increases to 2048. This makes me want to explore small batch size training for this project. Jeremy Howard tweeted that stable, low batch size training isn't easy, but it's a good plan. I want you to help me answer 2 questions in this chat. 1, why is stable, low batch size training difficult? And 2, what techniques are there, either in literature/archive, blog posts, or forums, to make low batch size training stable? I'm most interested in improving the accuracy of low batch size trainings. And so it had this 22-page report, including the references. Some of it was repetitive in its sections, and the conclusion was kind of repetitive, but it was great. I think overall it was a really helpful report, and I'll kind of walk through what I learned from it. So here's the executive summary. I'm not going to read the entire thing, but what I'm highlighting is that, this training regime of small batch size offers improved model generalization, and overcoming the instability of batch normalization is a critical first step, which can be done with things like group normalization. Careful management of learning rates improves stability and accuracy. The choice of optimizer itself is important, and then regularization strategies are also important and helpful. So right from the bat, I can see some clear directions on what I should look for, and ultimately these are the directions that I'm going to look at. But let me show you how I kind of explored this in my own way. So I go back and I look back at my results, and I can see that, yeah, there is an improvement for small batch size training, right? You go down from 256 to 816 or 32, depending on the model, and you're going to get, with the right learning rate, you're going to get a maximum accuracy. But there's also a trade-off, because you have a smaller batch size resulting in more gradient updates, and that takes a longer time to train. So especially at very, very small batch sizes of like 2, my training time was significantly longer. So I just had to like kind of run this, overnight and then let it finish. Otherwise, if I did a batch size of 2048, obviously it was a lot quicker. So there's that trade-off between more updates and longer training time and slash, GPU underutilization. And Jeremy tweeted that we covered this in some of our earlier courses. Lower batch size provides more updates, which should give better results for a fixed number of epochs. And this fixed number of epochs is important because on the Imagenette leaderboard, which is on the FastAI repo, there is a fixed number of epochs for each kind of bracket. So there's a 5 epoch range, there's a 20 epoch, 80 epoch, 200 epoch. So what I'm doing is I'm participating in the 5 epoch leaderboard segment. And so I'm going to have a fixed number of epochs, and therefore, if I lower the batch size, I'm going to have more updates compared to a larger batch size. So there's that trade-off of performance versus training time, which is a very real trade-off, especially as the data set gets larger than this kind of more flexible Imagenette data set. And then Gemini goes on to say that small batches can lead to gradients that are, quote, bigger and chaotic because an incorrect prediction on a single data point within a tiny batch can result in a disproportionately large loss and subsequently a large gradient update compared to its effect in a larger batch. Higher gradient noise stemming from the limited data used for each estimation leads to more volatile and less precise parameter updates. So at this point, I had this kind of gut feeling. I'm like, if I can visualize how cross-entropy loss interacts with batch size, then I think I can gain a little deeper tuition for this. But to be honest, I needed a refresher, so I went back to chapter 5 of the FAST book, and I've also wrote up a blog post and video walkthrough of cross-entropy loss explained. And it was, this is the 3rd or 4th time that I've gone through that chapter, and each time I get a deeper understanding of how cross-entropy loss works and what the intuition behind it is, what's the relationship between sigmoid and softmax for the binary class situation, and a lot of other kind of details that were really fun to look at. So that's there if you all are interested in looking at that. But here I'm going to look at a concrete example. So let's say I have a batch size of 2 and I have a binary classification task. And let's say these are the activations that are generated by the model. And let's say that for the first batch item, the target is the first class, which is class 0. And the second item, the class 1, is the target. So I'm intentionally making this batch item prediction incorrect. And not only is it incorrect, right? The activation for the target class is not the maximum. It's significantly lower. It's very confidently incorrect because the incorrect class has the very high activation, relatively speaking. So I'm trying to simulate this example where you have a batch item, you have a very small batch, and the batch item and the model is very wrong about the prediction for that one batch item out of two. So I pass the activations and the target tensor to cross-entropy loss, and I get a loss value of 4.7. Then I do the backward pass, and I look at the gradients. So we have negative 0.5, 0.5, 0.13, negative 0.13. So these are kind of our reference points. A batch size of 2 with a very, very wrong prediction, we get this loss and we get this set of gradients. So I'm going to now take those two batch items, and then I'm going to add 6 more, just kind of random activations. And then I'm going to add my 6 labels as well. So now I have a batch size of 8. I've quadrupled the batch size, but I still have this one, very erroneous prediction. I pass it through the loss function again, and you can already see my loss has dropped from 4.7 to 1.6. And then let's do this again. And then if I look at the gradients, I've gone from 0.5 to 0.125. So, a 4 times decrease of the gradients. So this was a very trivial example, but I think it was really awesome for me to see. It gave me a very concrete example and intuition of how a small batch size with a wrong prediction can cause noisier gradient updates, right? You increase the number of items in the batch, and then when you take the mean value of the loss function, because you have more items, it gets smaller, and then because the loss is smaller, the gradient update is smaller. So quick aside on cross-entropy loss. I'll highlight some things Gemini said in the report. On one hand, the noisy gradients can cause the optimization process to oscillate significantly around an optimal solution, making it challenging for the model to settle into a good minimum and potentially slowing down overall convergence. So noisy gradients, hard to find the right optimal solution. On the other hand, this very noise and the resultant exploratory behavior can be beneficial. The stochasticity introduced by small batches can act as a form of implicit regularization, helping the model to escape sharp, narrow local minima in the loss landscape and instead find flatter, broader minima. So there's a couple of pros and cons that are kind of pushing and pulling when you look at small batch size. On the pro side, you have faster updates and you have this implicit regularization. And then on the negative side, the cons, we have longer training time, we have GPU underutilization, you're oscillating around minima, and you have these chaotic gradients, this high gradient noise. And that pairing of pros and cons, I think, is exactly what makes small batch training a fascinating topic for me, because there's nuance involved, and that nuance interacting with models, interacting with learning rates and hyperparameters, just makes it a lot of interesting exploration opportunities for me to execute. So let's take a look at, what are some additional issues with small batch size, especially for these xresnet and xresnet models, which have batch normalization. So in addition to making the gradient noisy, small batch sizes make batch normalization statistics noisy as well, because batch normalization standardizes the activations within a network by calculating mean and variance statistics per batch. When batch sizes are very small, 1, 2, or 4 samples, these batch-wise statistics become extremely noisy and unreliable estimators of the true population statistics across the entire dataset. So there's 2 ways that batch normalization introduces noise. And I'm just going to switch to the group normalization paper summary that I did. That is also a video on my channel. So for small batch sizes, for batch normalization, per batch statistics become noisy. So you can have 1 or 2 images that are outliers, like we had in that example, and that drastically skews the mean and variance for that batch as we saw in our example, very confidently incorrect prediction lead to a larger loss and larger gradient. Also leads to a larger, mean and larger variance, especially when it comes to just looking at 2 items in the batch. So that's a per batch noise. But then there's this additional noise that batch normalization has. And the reason is that batch normalization has a running average, a moving average that is calculated so that when you do inference, whether that's during the evaluation step during training or inference after the model is trained, you're using the mean and variance, that's the moving average versions, for your input image during inference. So a series of unstable, high variance updates will cause the moving average to be less reliable of an estimate of the true population statistics. So ultimately, this moving average is trying to capture an estimate of what is the full data set's mean and variance during training. Obviously, we can't get that because we're not processing the full data set at once. And so batch size becomes a huge factor because as batch size decreases, each subsequent update can fluctuate because small outliers or 1 or 2 outliers in a small batch can cause the mean and variance to fluctuate. So you have per batch noise, 1 or 2 outliers drastically skewing the mean and variance for that batch. And then you have across batch noise because this moving average becomes noisy because you have this up and down fluctuation. So 2 sources of noise in batch normalization. The reason that batch normalization fundamentally is so sensitive to the batch size is because, as the name suggests, we're normalizing along the batch dimension. And so if the batch size decreases, the number of images decreases, now you're normalizing across a fewer number of samples. And so you're going to have those spikes that you wouldn't have, as we saw when we increased the batch size from 2 to 8, the kind of noise across the batch decreased in the form of a lower loss and a lower gradient. So if we look at the values or the models that I'm working with, they all have a considerable number of batch normalization layers. So xresnet 18 has 22 batch norm 2D layers. xresnet 34 has 38. So if we just run that and run that. And then my XSE ResNext 50 has 55 batch norm 2D layers. So obviously these are going to be very significantly impacted by batch size. So that's the problem. In addition to the original trade-offs we saw, you have faster learning, you have this implicit regularization. On the other hand, you have longer training time. You have a likelihood that you'll miss the local minimum, the optimal solution, because it'll oscillate. And then you have this gradient noise. On top of that, with batch normalization, you have this additional 2 sources of noise that are dependent on the batch size. So this is a kind of nice summary of Gemini on how to address this. Addressing the challenges of small batch training requires a multi-pronged approach, focusing on adapting learning rate strategies, rethinking normalization layers, selecting appropriate optimizers, and employing advanced gradient management and regularization techniques. And ultimately, those are the directions that I'm going to pursue. But let's look at in some detail what Gemini said about some of these solutions. So starting with learning rate. For small batches, the high gradient noise often necessitates smaller learning rates to prevent divergence and ensure stability. And I actually saw some evidence for that in my Imagenette experiments. So here's my xresnet 18. The green line is 1e-2, and the orange line is the 10 times smaller 1e-3. And if you look at around 10, you have this kind of trade-off where for batch size is smaller than 10, so that's 1, 2, 4, and 8, the lower learning rate results in a slightly, but not insignificant, higher accuracy. So I do see that evidence that this high gradient noise necessitates smaller learning rate to prevent divergence and ensure stability. And I see that here as well. This brown line is 1 enig 2. This purple line is 1 enig 3. 1 enig 3, the smaller learning rate, has a higher accuracy for small batches. And I see that considerably here, especially for some of these kind of larger small learning rates. Here is, what is this one? This is 1 eneg 3. And then this brown line is 1 eneg 2. And you can see a considerable, oh, actually, no, even for smaller batch sizes, you see a considerable difference in accuracy, right? For a batch size of 8, the 1 eneg 3 learning rate has a like 75% accuracy, whereas the 1 eneg 2 learning rate, that's 10 times larger, has a 65% accuracy. Oh, no, sorry, I'm looking at the wrong line again. 55%. So there's almost a 20% difference in the two learning rates. And so I think in this model in particular shows evidence that smaller batch sizes benefit from a smaller learning rate. Additionally, small batch sizes, 2 to 32, can be more robust to learning rate choices. So if we go back up here, let's start up here. So if we look at kind of this regime, so here's 10 to the 1, 20, 30. So here's 32 and below. If we look at the difference between the learning rates here, it's not insignificant, but it's considerably smaller than the difference in accuracy between the learning rates at larger batch sizes. So I do see here that at least for xresnet 18 and xresnet 34, I do see that small batch sizes are more robust to learning rate choices. I also see that, I see that less so in xresnet 50, resnext 50, because this one is a bit of an outlier, because as you can see here, as the batch size increases, the accuracy for the different learning rates is pretty stable, right? There is a difference across them, but you don't get that drop off, considerable drop off down to 20% accuracy and down to almost 0% accuracy as you do for the xresnet 18 and 34 models. So there is a little bit of nuance in the behavior based on the models. They also talk about learning rate warm-up strategy. That's already the default when I'm using the vision learner, but I didn't play around with any of those hyperparameters, like what number of warm-up steps, for example. And ultimately, it gets to this next idea about addressing the batch normalization problem. So it says batch normalization's mean and variance computation introduces uncertainty caused by the stochastic batch sampling, which helps regularization. This uncertainty is missing in group norm, layer norm, and instance norm, but it is possible that group norm combined with a suitable regularizer will improve results. This can be a future research topic, assuming this is already done as research, because this was in 2018. But ultimately, there's again this trade-off, right? Batch normalization has two sources of noise. Per batch noise, one or two outliers are skewing the mean and variance, and then across batch noise, fluctuating mean and variance statistics cause the moving average to fluctuate. But it's that very fluctuation that kind of introduces this additional type of regularization, and it causes the batch normalized model to generalize better. On the flip side, if you use group normalization, they found that group normalization resulted in a 10% lower error rate than batch normalization for small batch sizes. And this is best illustrated by this diagram, if I can find it, in the group norm paper. So let's zoom in a bit. So here we have batch norm. N is the number of items in the image. C is the channels. H and W are height and width. So batch norm is calculating mean and variance across the number of items in the batch. So if N decreases, right, you have a smaller batch size, batch norm statistics are going to be affected. On the flip side, you have group norm, where it's a single image and multiple channels across which the mean and variance statistics are calculated. So group norm is independent of batch size, right? Because it's only operating on a single image. Similarly, instance norm and layer norm are kind of the two extremes of group norm. Instance norm is saying, instead of a group of channels, what if we looked at just one channel for that single image and then calculated the mean and variance. Layer norm is saying on the other side of the spectrum, layer norm says, what if we look at all channels for that single image and we calculate the mean and variance? But ultimately, the main point here is that layer norm, instance norm, and group norm all are giving the same kind of batch independence because they're only relying on a single image. The group normalization paper did find that layer norm and instance norm perform worse than group normalization, so you don't get that 10% lower error rate than batch normalization. But, it's still worth trying because I have different models and I have a different data set than what they used in that paper. And finally, Gemini suggests to try different optimizers and tuning their hyperparameters and trying different regularization techniques like weight decay or data augmentation. And these are things that I already wanted to try kind of coming into this project, and I'll talk about that a little bit at the end. I just want to highlight again that regularization in tandem with group normalization is recommended to try to get back some of that implicit regularization that batch norm had because of that noisiness of the mean and variance statistics. So what are my next steps? The main thing for me is I'm going to replace the batch norm layers with group norm in all three of my models and then run the same experiments, except this time I'm just going to focus on small batch sizes. So I'll do either 2 to 64 or maybe even 2 to 32. Based on how that goes, I'll add a regularization method like weight decay and try different values of weight decay and see how that interacts with group norm. And then based on how that goes, I will try out different optimizers using Benjamin Warner's Optimi library, which is a library that I've been meaning to try for a while. And this is a great opportunity to do so. And then one thing I actually left out here, which I'll add, is that I also want to try out different data augmentation strategies, which is already in FastAI, but there's also some additional data augmentation for vision and other modalities. But for me, I'm caring about vision right now. But Benjamin Warner's FastExtend library also has a bunch of vision data augmentation. Because we have a small number of epochs, I'm only doing 5 epochs, I don't expect data augmentation to really work. However, the one kind of caveat is that this implicit regularization that batch norm had that we're trying to get back with group norm by adding regularization, that's one potential avenue where data augmentation might improve performance. But again, we'll see. And of course, at each step, I'm going to use the LR Finder to find 3 learning rates that are stable for that batch size and for that model. And then, we'll see. I'll run the same experiments as I did before. So let me just go down to my training code. So I had this training loop where I have my batch sizes. I loop through them. I loop through my models. I loop through my learning rates. I set up my weights and biases log. And then I instantiate the learner based on the model. And then I fit one cycle for 5 epochs and for the learning rate and finish logging. So same kind of process. I'll just reuse that code for these learning rates and batch sizes and these models. So that's it for this video. I'm going to continue documenting this Imagenette experiment exercise / project. It's turning more into a project now over the next few weeks, maybe even longer, depending on how long these experiments take. I'll be posting it on my blog and making YouTube videos as well. So thank you for sticking around until the end. Thanks for watching, and I will see you next time.